Okay, this is section 8.4, and it's called, and this is weird, it's going to seem weird, this is the hard part to get, it's got to get dumped into your brain a little bit here, it's kind of hard to understand. But it says finding sums of infinite geometric series. It means we're going to let a series be geometric, I'm going to let it go on forever and ever and ever and ever and ever and ever, and we're still going to be able to add it up and get a number. Under certain circumstances. That's the killer. If you just take the formula I'm going to give you in a few minutes and you just blindly apply it, you will miss more than half the problems. Well, a lot. You'll miss a lot. Because if you have a geometric series where every successive number gets bigger and bigger like this is the classic one. Series we're talking about, which is plus signs. 2, 4, 8, 16, and so forth on into infinity. There's no way you can add that up. Because the numbers just keep getting bigger. The sum of that infinite geometric series is infinity. And that's not a number. But a series like this one, 27 plus 9 plus 3 plus 1 plus 1/3 plus on into infinity. That does have a sum. A very particular one. People go, no. People say, no, that can't be because every time you put the next number on, it's smaller than the one before, but it is something. And so if you add it on, surely the number's getting bigger, right? Listen to this. This is called Xenos Paradox. Zeno, by the way, here's a really cool thing. Have any of you ever heard people on TV or giving a lecture or something, parents, whatever, say circa 300 BC? Or they say circa. You know what that means? It literally means approximately because circa means around. So when we say, in common regular language, we say it was around 200 BC. People say circa means around. That's what circa means, is to go around, circumference. So circa 300 BC means around 300 BC. It's just a very academic way of saying about that. But anyway, that comes up right here. It says Zeno of Alg, circa 450 BC. 450 years before Christ. How long has our country been around? 250 or so years. I mean, it's 200 and some years, right? 1976 was 200 years. We're getting there. Huh?
You said 1976.
Oh, 77. No, in 1976, we've been around for 200 years.
Yeah.
Yeah.
Oh, yeah. Okay.
Yeah.
That's
Okay.
interesting.
And so 200 and some years. This is 450. This is almost twice as long as we've been around, just as a country. So this is a long time. This was before Christ, for heaven's sake. This was a long time ago. Okay. Zeno of Alg, 450 BC, is credited with creating several famous paradoxes. But by far the best known is the paradox of the tortoise and Achilles. You've known it as the tortoise and hare. Just the tortoise and Achilles. Achilles was the great Greek hero of Homer's The Iliad. Anybody ever see Troy? Rated R, so probably not. Scott, what's his name?
Rated R for rad part.
Yeah. No, I can't remember what his name is. It's one of the most famous actors in Hollywood right now. Ready to Angelina, or was Angelina Cooper. Brad Pitt, yeah. Gosh, I can't remember his name. Anyway, Brad Pitt played Achilles in that. Wasn't too bad. Why? I don't like him as a person, but he's good actor. Anyway, here we go. So Achilles was Homer's hero in the Iliad. He was an extremely good athlete, great at throwing spears, tremendous soldier, good fighter. Anyway, it has inspired many writers and thinkers through the ages, notably Lewis Carroll. You know Lewis Carroll? Do you have any idea what Lewis Carroll wrote? Through the Looking Glass? Alice in Wonderland? That's what Disney called it, but he called it Through the Looking Glass. Let's see. Douglas Hofstadter, who also wrote dialogues involving the tortoise and Achilles. Anyway, I don't know who Hofstadter is. But anyway, a lot of people took this single paradox and wrote different things, made different movies. So it's a big deal. The original story goes something like this. This is, again, apocryphal, like it was with with Gauss the other day? You know, means this probably isn't true. Very likely not true. But still, there's a point to be made. So listen up. Here's the story. Try to think about what's going on. The tortoise challenged Achilles to a race, claiming that he would win as long as Achilles gave him a small head start. Achilles laughed at this, for of course he was a mighty warrior and swift of foot, whereas the tortoise was heavy and slow. How big a head start do you need? He asked the tortoise with a smile. 10 meters, the latter replied. Achilles laughed louder than ever. You will surely lose, my friend, in that case, he told the tortoise. But let us race if you wish it. On the contrary, said the tortoise, I will win, and I can prove it to you with a simple argument. Go on then, Achilles replied with less confidence than he felt before. He knew he was the superior athlete, but he also knew that Tortoise had a sharper wit. And he had lost many a bewildering argument with him before this. Suppose, began the Tortoise, that you give me a 10-meter head start. Would you say that you could cover that 10 meters between us very quickly? Very quickly, Achilles affirmed. And in that time, how far should I have gone, do you think? Perhaps a meter, no more, said Achilles after a moment's thought. Very well, replied the tortoise. So now there is a meter between us, and you would catch that distance very quickly. Very quickly indeed, and yet, in that time, I shall have gone a little way further. So that now you must catch that distance up, right? Yes, said Achilles slowly. And while you are doing so, I shall have gone a little ways further. So that you must now catch up the new distance, the tortoise continued smoothly. Achilles said nothing. And so you see, in each moment, you must be catching up the distance between us. And yet I, at the same time, will be adding a new distance, however small, for you to catch up again. Indeed, it must be so, said Achilles wearily. And so you can never catch up, the tortoise concluded sympathetically. You are right as always, said Achilles sadly, and conceded the race.
So you can pass him.
Well, of course you can. You've seen it happen. Achilles knew he could. But he bought the argument, and so did everybody who was listening to it. Zeno, the guy that actually told these stories, flummoxed a lot of people. Regular, good-thinking, quality, productive people. Not just people that don't know how to think, like Achilles. Because the tortoise is always adding a bit more, and when he catches that up, the tortoise will go a bit further. In other words, if you're adding up stuff like this, and you add on what would be next? 127th?
Yeah.
And then 181st? And then 1 over 162? It's not very much. It keeps getting smaller what you're adding, but you're still adding something. So surely the number this adds up, surely the number that we're adding to is getting bigger and bigger and bigger because you're adding just a little bit more every time. Is that right? Yeah, see, you sucker for it too. It's not a hard thing to believe. Now listen to another version of this. I'm going to stand over here and show you what I mean. This is often the way it's told. It says Xenos Paradox may be rephrased as follows. Suppose I wish to cross the room. I want to cross the room, get out that door from here. First, of course, I must cover half the distance. Okay, covered half the distance, right? Then I must cover half of that distance. Then I must cover half of that distance. Even if I don't stop, I'm still doing this, covering half the distance, right? Then I must cover half of that distance. Then I must cover half of that distance. And then half of that. And then half of that. And half of that. And half of that. And I can never really reach the door because I keep adding a little bit more and I can never get out. We're stuck in here forever, people. Because you have to keep adding more and more and more and more. The thing was, folks, is that people bought into the argument that, well, we're still adding something. So surely what we had before, the number's getting bigger. You're right. It is getting bigger. But it's approaching a definite number. Watch this. Consider this up here, and this is going to get really quite exaggerated here. If I'm on a number line, let's say right here, and this is 0, and way, way out here is the number 1. Okay? Hang on here, look. This is like the distance across the room. So if I go from here to about here, we'll say that's a half, right? So I've now gone half. To that, I'm going to add half of that, which is what? A fourth. To that, I'm going to add half of that, which is an eighth. And then I'm going to add half of that, which is a 16th. And then half of that. Now watch. And then I'm going to add half of that. And then 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 half of that. And half of that. And half of that. Doesn't it?
Yeah.
It just equals 1. Because I just keep cutting it in half. I never pass the 1. I just keep getting closer and closer and closer and closer. And every time I add another half. So if I add them all up, you don't get a bigger number. You get 1. In this case, you get 1. This is why it's possible to get out the door today. This is why it's possible for Achilles to beat that tortoise in a couple of seconds. Because people are under the impression that if you keep adding a little bit more, even though it's really small, that you just keep making the number bigger and bigger and bigger. You don't. You keep making the number bigger, approaching a definite number, not infinity. Do you understand what I'm saying?
Yeah.
Now, let me show you another way to go about this based on what you learned the other day. Take a look at this up here. I'm going to erase some of this so that I can stay on camera here so people can see it. This is what we had for the sum of a finite geometric series the other day. We've been working with it already today. Remember what it is? Anybody have it memorized? Please don't look it up. Tell me from memory. The sum of an infinite geometric. This is geometric. Starts out A1 times 1 minus R to the just n. This is the sum one, not the nth term one. Yeah, the nth term one's n minus 1, but this is just n over 1 minus R. Now, I'm going to come back to what I started with at the beginning. Remember I said if you have the sequence 2 plus 4 plus 8 plus 16 plus 32 plus 64 and so forth, there's no way that you can find a number that's approaching, right? And the difference between that one, just a minute, that one, 16 plus dot, dot, dot. That one has no sum. We say, that's what we say. This has no sum. Because it's too big. It just keeps getting bigger. But this one, we decide, does have a sum, don't we? Didn't we? And that sum was 1. Okay. The difference between this sequence and this one is what?
The one's going down. That one's getting huge.
One's going down and the other one's going up. More specifically, as far as geometrics go, what is the R for this one? What is the R for this one? Now, it's because this is a proper fraction. It could have been 5/6. As long as it's a proper fraction. Anytime you multiply a number by a proper fraction, doesn't that number get smaller in the result? Yeah. When you multiply, right? So if R is a fraction, these numbers are going to be going down, down, down. If R is greater than 1, an improper fraction over a whole number, anything greater than 1, every time you multiply by something greater than 1, the number gets bigger, right? You get a geometric sequence that has no sum. It's all about the size of R. Please turn around. Shh. It's all about the size of R. Now think about this with me for just a minute. This is a thought experiment. You're going to have to stay with me and think hard. If I use this sum formula right here, and I use it for a huge value of n, say right there. If R is between, if R is a proper fraction, meaning, that can be equal to -1 to 1. That's a proper fraction. Could be negative. It's okay if it's negative. I'll show you that one in just a minute. But as long as R is between here and here, then this thing right here that's used this many times, can you understand that if you take 1/2 times 1/2, you get a 4th? If you multiply that times 1/2, it gets smaller yet. Every time you multiply by a half, this number right here gets smaller, doesn't it? Yeah? Until as n gets huge and gigantic, this number right here having been used 150 times, is the result of taking a half of the half of the half of the half of the, that number is virtually zero. Do you agree?
Yeah.
As n gets bigger, it gets closer and closer and closer to zero. So what I have then is a1 times 1, because that's 0, over 1 minus r. So as n gets bigger, this is what we say, as n goes to infinity, Sn goes to 1 or a1 over 1 minus r. Would you buy that?
Yeah.
That's our formula for today. Very easy formula to use. You need two things. You need to know the first term, and you need to know r. And that's it. So let's see if that works on this one that we claimed was 1. Sn would be a1 over 1 minus r, which is also a half. What is 1 minus a half? A half. What's a half over a half? 1. You follow me there? Okay. Now let's try something a little tougher. This half thing was easy to work with, but it was important that it be easy for you to kind of understand the concept. So what I want to know is, what is the sum of an infinite series whose first term is 14 and whose r is 4/5? First of all, will this have a sum?
Yes.
How do you know? Because what's a proper fraction? The r. The r is less than 1, right? So to figure out that sum, we just say s, and we don't say n, by the way, folks. We say infinite. People are such a distraction. You don't say Sn anymore. You say S infinite. Means the sum of infinite terms is going to be equal to 14 over 1 minus 4/5. What is the problem? What's 1 minus 4/5? So we have 14 over 1/5, which is the same thing as 14 times 5, yeah? That one happens to add up to 70. Does that make sense to you? It's not a very difficult thing to use. Let's try another one. What would be Sn? See if you can figure this one out. Sn, if the first term was, not Sn, S infinite. If the first term was 7 and r was 1.5, what would it be?
It would be infinite. So infinite.
Yeah, right. So we say no sum. We don't actually use infinity because it's not a number. Okay? We say no sum. Why is it no sum? This r is not a proper fraction. It's greater than 1. R is greater than 1, so this will not have a sum. But if you don't recognize that, you can still apply the formula. So which is correct? No sum or negative 14? No sum. This thing will still apply. You can still plug it in. If you don't remember that this thing has to be a proper fraction for you to even use that formula. Okay? So I'm going to summarize this for you again now that we've kind of developed it. This is what we say. S infinite equals a1 over 1 minus r. If, all right, guys, take your stuff and get out until you can calm down. If the absolute value of r is less than 1. When I say the absolute value, I mean it could be positive or negative, but it has to be a proper fraction. You follow me? So what if r is, instead of this one over here, this one doesn't work, by the way. If r is, we'll start at 7 again, and r is negative 2/3. What that means, folks, is that every time you multiply a number, like for example, let's start out at 7. You multiply by negative 2/3, you get negative 14/3, won't you? You following me? 7 times negative 2/3. Then you take that times negative 2/3 and you get a positive 28/3. Right? So it keeps bouncing back and forth from a negative to a positive. This is minus, this is plus, this next one will be minus. Because every time you multiply a number by a negative, if it's a negative, you get a positive. If it's a positive, you get a negative. So it keeps alternating in sign. So what that does on the number line, in case it worries you at all, is we start out here at 7, then it jumps down to negative, say 0 is right there. It jumps down here, and then it jumps up to 28, and then it comes over to here, and then over to here, and then over to here. And it settles somewhere. Right? But it keeps going like this, and it keeps bouncing in like this, because these fractions keep getting smaller, and it keeps bouncing in. Closer, closer, closer. Doesn't mean it's going to be 0. I'm just saying it jumps across the 0, hits a number on it, then comes back, then we add this number, then we add this number, then we add this number, then we add this one. We keep adding smaller and smaller ones. So it's okay, even though it's alternating in sign. So this would be what the sequence looked like. What would its sum be? What's the sum of infinite stuff here? It would be what? 7 over.
1 minus 1.
So 1 plus 2/3, right? Because it's 1 minus negative 2/3. Y'all follow the plus sign?
Yeah.
Okay, so that's 7 over, that's 3/3 plus 2/3 is 5/3? Yeah? And we would divide by a fraction, we multiply it by its reciprocal. 7 times 3/5 would be 21/5 is what they add up to. So long as this is between -1 and 1, or its absolute value is less than 1. Okay? I should say this. Well, no, its absolute value is less than 1. That's good. That stops it at 0. Well, I should say this too. Must be greater than 0, because if it is 0, that's stupid. Multiplying by 0 gets you to 0 in a big fat hurry. Okay, so that's a big, huge if. Watch for those R's and make sure R fits the bill before you start applying the formula. Because the formula will work if you do the wrong answer. If R is greater than 1 or less than negative. Y'all follow me? All right, so let's take a look. Look at example 2. Look at example 2, please. On page 437. Example 2 says there's 3 different things, 3 different presentations of different geometric series. The first one's offered with a summation notation. Notice that the top number is not a number, it's infinity. It means you're going to do an infinite geometric series. So I want you to look at what you're seeing there, example 2. Can we actually add that one up? What do you need to know to answer that question? You need to know R. Can you see what R is in the A part of example 2? What is it?
0.7.
0.7. So can we use our formula on it?
Yes.
Yep. What is the first term?
1. Oh, 3.
Is it 3?
No, 3 times 0.7.
No, look at it. It's 0.7 to the 1 to the I minus 1. If I is 1, you get 0.7 to the 0, which is 1 times 3 is 3. So the first term is 3. That goes there. And the common ratio is what?
1 minus
0.7, which would be 3 over 0.3, which is, really? You need a calculator for that?
Oh, sorry. My brain is.
Okay, that's all right. Okay, so that one was add upable. How about the B part? What will it add up to? No sum. What is R for B? 3, right? Let's see how it's no sum. Okay, how about for C? What will that add up to? First of all, what is R? R. Is it?
I think it's -3/4. -3/4.
Yes.
How do you find out?
You plug it in.
You take any term divided by the one before it, don't you? Is that how you find R?
Yeah.
Any term. I'm going to take 9/16. So I'm going to take 9 divided by 16, enter, divided by the one before it, which is parenthesis -3 divided by 4, close it. You can make your calculator do it. You're right. It's -3/4. You see how we found that? Does that fit the bill for R in order to use the formula?
Yes.
All right. So So R is negative 3/4. What's the first term? 1. So the sum of infinite is going to be 1 over,
1 minus negative 3
which is
plus 3
1 plus 3/4. That's 1 over. This is 4/4. This is 4/4. 7/4 equals 4/7. So that didn't add up to much, but that's what it adds up to. Y'all follow? Okay. Look at example 3. This one gets a little bit crazy. Example 3. Believe it or not, this is another experience with Xenos Paradox that may stump you for just a minute. Talking about a pendulum. It would be the same if we were talking about one of those really, really bouncy rubber balls. Whenever you drop any kind of a ball, it will never return to its original height, right?
Right.
So some fraction of its height. So here's what it says. A pendulum that is released to swing freely travels 18 inches on the first swing. On each successive swing, the pendulum travels 80% of the distance. This is under pretty high friction. 80% of the distance of the previous swing. What's the total distance covered by the pendulum? You're going, well, we can't be. It's just going to keep going like this. It'll just get shorter and shorter and shorter.
Well, then just that.
Except for this is a infinite geometric sequence, right?
Yeah.
Okay, it's like a kid on a swing rather than a pendulum. Take a kid that tends to have a lot of friction in it. You give the guy a really good kid a really hard push. Pretty soon he'll come to a complete stop, right? The question is, in the process of stopping, how much distance did you travel? Okay, that's what we're asking. And they gave you all of the information you need there. The first term in the sequence would be what? 18. What would be the next one?
0.8. Or, no.
18 times 0.
What is what? By the way, you don't have to do what I'm doing here. I'm just showing you. What's 18 times 0.8?
14.4.
14.4?
Yes. Yeah.
Okay. Now take that times 0.8.
11.52.
So you can see this pendulum's not going as far every time. It's like a kid on a swing, like I said. Every time it goes through, it goes a little bit shorter because of friction. But it's going to go, believe it or not, if you really think about the theory of it, it's going to go forever. It's going to continue swinging forever. You're going, the kid eventually stops. You're right, it does. That's because of our imperfect world. But we can figure out how far, at the very most, this kid would swing. By taking 18 divided by 1 minus 0.8, which is 18 over 0.2, which is 90. 90 what? Whatever they were measuring it in. Centimeters?
Inches.
90 inches total. Even though it can theoretically continue swinging forever, it will never cover more than 90 inches. Okay, so take a look at example 4. This one I'm just going to tell you the facts on. They want you to make a geometric sequence out of it. I don't think it's necessary. I think it's ridiculous. I'm going to tell you some things about repeating decimals that hopefully you'll carry through for a while in your life. This number right here, 1 divided by 9, is, anybody know? Can you find out? Do it. 0.1 repeated. What is 2 ninths? 0.2 repeated. What do you suppose 3 ninths is?
I'm assuming it's actually 1/3, so.
Yeah, this is 1/3, and you know 1/3 to be 0.3 repeated. It's because it's 3 ninths. You following me? Okay, so I bet you 4 ninths is what? 0.4 repeated. 5 ninths again? No, this is getting boring. 0.5 repeated, right? Well, what do you suppose then that 40 99ths is?
4 repeated.
Check that out.
40. 40 repeat.
Yeah. It's 0.404040, right?
Oh.
So what do you suppose 327 over 999 is? Yeah, it is. You can check that out. Okay? So anytime you have, let's see if you can reverse it. If I have 0.3824 and then 3824, and you notice that's repeating, what fraction is that?
1,802.49999.
And you can check it out, see if that works. So if the decimal begins to repeat right after the decimal, take that repeated stuff, whatever, before it starts again, however many that is, and however many places you have, put it over as many nines,
Good to go.
and you've got the equivalent fraction. Okay? You following that? Just for the sake of argument, what happens if it doesn't begin to repeat right after decimal? And by the way, you won't run into this idea on the ISAT or on your final, or on your test or anything, or on this exercise. It'll all be about stuff like this. If you can figure out how many digits are repeating before the next block starts, put that number, that repeating stuff, over as many nines and you'll have the fraction. You should reduce it if you can. Your calculator can do it. Just put 40 over 99. You hit enter and then you go math, enter, enter, and it will tell you what the reduced form is, and if it reduces. Okay? But here's something interesting. If you have a number like this, 0.137927272727, you've got something that begins to repeat back here after these guys. This is called a rational number, and rational numbers by definition mean that you can write them as one number over another. That's their definition. So the question is, what fraction belongs to this? There is a fraction that goes with this because this is going to 7 forever. But it doesn't start to repeat till 4 digits later. Let me show you this really cool trick to finding this out if you ever have to do this, if you have to prove it. If I let n equal this number that I'm looking at, do you understand that 10,000 n equals this? Right? Moves over 4 places if there's 4 zeros in your multiplier. Now, if I subtract the two, now I've got to put this under here so we can see the subtraction. If I subtract those two, I'm going to put it like this so you can see it. And so forth, like that. If I subtract this side, I get 9, 9, 9, 9, n. Right? If I subtract this side, okay, wait just a second. I gotta do this a little differently. No, I don't. 2, 7, 2, 7, 2, 7, 2, 7. If I do that, then these are all going to subtract out, right? These will all subtract out. These will, this one, this one, this one, this one, this one. And then I've got this. So now I need to take 1379.2727 and subtract 0.1379. Do that. That's not what I wanted to do. There's something wrong with this. I haven't done this for such a long time. I remember the concept, but I'm doing something wrong here. What do you get?
1379.1321.
And I still don't want a decimal, so I've done something wrong here. Oh, I know what I did wrong. Okay. Do you want me to continue to show you this? Okay, hang on a minute here. We have to do two things. Here's the deal. This is the n that I want to deal with. If I multiply by 10,000, like I said, I get this. But then I want to multiply by 2 more zeros than that. That would be 1,000,000. Well, it's got to have 6 zeros. That's 1,000,000. Wouldn't that be, if I multiplied that by n, wouldn't that be 137,927.27 repeated? And now if I subtract those two, this one and this one, I'm bringing this down here to subtract. That would look like this. 9.27 repeated. Then these subtract, clear out, and you have this minus this, which is two whole numbers. Okay? So now, take this minus this and tell me what you get. That's a whole number. What is it?
1, 3, 6, 5, 9, 8.
Okay? And what happens when you take 1,000,000 minus 10,000?
You get less than.
Okay, if you don't know what it is, you can't do it in your head, then do this subtraction. What do you get? 900,000?
It should be 900,090. 1, 2, 3, 1, 2, 3. 990.
There's 3 9.
There's three nines?
There's
I got 2
3 9.
9s and 9.
Wait, hold on. You got 1 0. There's 4 0.
Like that?
Yeah.
Now, that's n right there. Now divide. N equals this number over this one. And they are both integers, which proves that it's rational. Also, you can check it. Take that number divided by 990,000 and see if you don't get this.
All right.
Is that what you got? No? Well, if all the subtractions were right, you should.
It's close. It's just not the same repeated.
What is it?
It says a 7 repeated.
Just 7, not
Just
2 7?
It's the same 0.1379 though.
And then it's just 7s after this?
Yeah.
All right. Well, the process is correct. I'm wondering if you guys did the subtraction right.
Pretty sure.
I'll have to look at that, but I know it works. It's worked in the past. There's a mistake in here. But anyway, that's what it's supposed to give us. The 2 7s. That's it. I'll work that out. See if I can figure out. That's how you show that any repeating decimal, no matter where it starts to repeat, this is how you show that it's actually a rational number. By it turns out to be one whole number over another whole number, which is what they just need to be integers. I'll figure out why that failed. Okay, so on example 24, or example 4, all this last part that's been, it says 0.24 is a fraction in simplest form. You would write what? What? 24 over 99. Does that reduce? It does too. There's a 3 in both.
Oh, there is.
8 33rds is how you would express that. Okay? So you have to reduce it if it's possible. And your calculator can do it if you don't know what it is. Do y'all know how to make that reduce? Do you know how to make your calculator reduce that fraction?
99 math.
Right. Well, 24 divided by 99, enter to get a decimal, and then math. Yep. And it'll reduce it for you. Okay, are y'all set? Okay, so this is the assignment for those of you doing it on paper. 7 to 15 odd. 16 to 19. 21, 23, and 30. That won't be too bad. You'll be all right.